Let's start with the second part of the descriptive chemistry unit. We are going to talk about types of bonds, Lewis structures, resonance, and Lewis acids and bases.
Now, what is a bond? A bond is an attraction between atoms that helps us make chemical compounds. We have different types of chemical bonds. It can either be a covalent, ionic, coordinate covalent, metallic, or hydrogen bond. The covalent bond can be a polar covalent bond or a non-polar one. What is a covalent bond? A covalent bond forms when two atoms share two valence electrons, one from each of the compounds or atoms, right? A polar covalent bond is when this bond is made between atoms that have different electronegativity, and they give place to dipole-dipole interactions. This electronegativity difference between the two atoms can be between 0.3 and 1.7. To determine if a molecule is polar, we have to follow several steps. Number 1, we have to draw the correct Lewis structure. 2, we have to determine the electron domain geometry and molecular geometry of the molecule. Remember, how you might draw the Lewis structure on paper is not always representative of how that molecule looks in 3D or in the actual life. Number 3, determine which bonds are polar. And 4, lastly, is to determine if the sum of the dipole moments of polar bonds cancels each other out. Now, a non-polar covalent bond, for example, is methane. The Lewis structure shows the electrons shared between the carbon and the hydrogen atoms. One electron is from the carbon, one electron is from the hydrogen. In these cases, the electronegativity difference between the bonded atoms goes from 0 to 0.3, which is very low. The majority of organic compounds have covalent bonds. Now, the molecules that are formed primarily by non-polar covalent bonds are often immiscible in water or other polar solvents, but they are very soluble in non-polar solvents, such as hexane or any other. Now, let's do a simple exercise. Let's determine if the following molecules are polar or non-polar. For example, water. The dipole moments of the OH bonds in water do not cancel. Therefore, water is a polar molecule. For example, BF3. In this case, the bonds the dipole moments cancel each other out. So BF3 has no net dipole. Therefore, it's a non-polar molecule. Anytime we have a central atom bonded to the same number of atoms, with all of them bonding, so there are no non-bonding pairs, the dipole moments will always cancel out and the molecule will always be non-polar. So, the question would be, what is the dipolar moment? A dipolar moment is when we have two electric charges that have the same magnitudes but an opposite sign, and they are separated by a certain distance. That's what makes a dipole. Now, the dipolar moment quantifies the dipole's magnitude, and it depends on the electron charge and the internuclear distance. Bonds can also have a certain polarity. We can have polar bonds or polar bonds. The ones that are apolar means that they have both charges exactly the same, so they compensate each other. But for a polar bond, one atom is stronger and pulls the electrons more to their side than the other one. Now, to know the molecule's polarity, all we have to do is try to compensate the charges and try to see where the vector would go, if we had a vector, of course. Now, for the first molecule in this slide, we have 4 chlorides, right? And just one carbon on the center. Now it's a non-polar molecule because the polarity is 0. All the bonds are making the exact same force, therefore equals 0. On the second example in this same slide, we have CHCl3. That means the hydrogen is pulling less than the chloride, and therefore the polarity is different to 0. Here we can see some apolar or non-polar polyatomic molecules, but also polar polyatomic molecules. Just have a look at them. Ionic bonds. Ionic bonding is a type of electrostatic interaction between atoms that have a huge electronegativity difference, right? So they are held together by the attraction of opposite charges. If the difference of electronegativity is over 1.7, it is likely to be ionic. But if it's less than 1.7, as we've mentioned before, it will be covalent. Just remember that. If we have a look at the sodium chloride example, we can see how the sodium ion has 1 positive charge, and then the chloride ion has 1 negative charge. That's why they can form an ionic bonding that is quite stable. In these ionic compounds, we find anions and cations, which have positive and negative charges, and then which are also electrostatic forces. If we have a look at the factors that influence packaging, we can see how the ion arrangement in ionic crystals has an impact. Now, for the molecule to be stable, the atoms need to be touching each other. They don't have to be, so the surrounding atoms don't have to be touching each other, but they have to be in contact with the central atom. If they're also closer, but also touching each other, that would also be stable. But if they're only touching each other, so the outside ones, but they're not in contact with the central atom, that would be unstable. So the electric neutrality of crystals must be respected. A solid solution is a crystalline phase that can present a different composition. Cations can be replaced with a different charge, or anions can be replaced by others with different charge as well. So this way, we will be forming vacancies. What are the ionic crystals' characteristics? That's a good question. Now, let's see. They're usually hard and fragile solids. They have a high fusion and boiling points. They have low electric and thermic conductivity. They have polar solvent soluble as water. They have high conductivity in solution. And when the UR increases, the hardness also increases. And they have a crystalline density that goes according to this formula. How is the conductivity of these ionic compounds? Now, because it's a solid, it is usually isolating. They are conductors in a melted state, and defects in the crystalline net can increase the solid conductivity. These ionic bonds can have different properties for which they're used for engineering applications, such as car components, exchangers, turbines, aerospace uses, etc., etc. Now let's have a look at a coordinate covalent bond. These ones are very interesting. They are formed when the two shared electrons come from the same atom, from the same molecule. That is different from what we've seen before in the different covalent bonds. So be careful. In this case, if we have a look, for example, at the boron trifluoride and ammonia, the nitrogen has a pair of electrons, and they are shared with an empty atomic orbital on the B. Metallic bonding is the force of attraction between valence electrons and the metal atoms. It is the sharing of many detached electrons between many positive ions, where the electrons act as glue, giving the substance a definite structure. It is unlike covalent or ionic bonding. The metallic properties are as follows. They are solids with crystalline structure. They have a relatively high thermal and electrical conductivity and can deform plastically under the application of a force. And they have a metallic shine that is a consequence of the high reflectance of light. So, as said before, metallic solids have a compact crystalline structure. And the crystalline structure is the periodic arrangement of atoms in a crystal, and is as follows in this formula: the crystalline density. The density equals the number of atoms multiplied by the atomic weight divided by the Avogadro number multiplied by the cell's volume. Now, an alloy is a mixture of two or more elements, but minimum one of them has to be a metal. A purpose is an improve of properties of pure metals, like mechanical resistance, hardness, or resistance to corrosion. For example, steel is harder than iron. A preparation would be by fusion of the components and rear mixture. Solid solutions are homogeneous mixtures where components are evenly dispersed. The minority metal atoms are distributed randomly between the majority of metal atoms. They can either be a substitute solid solution or an interstitial solid solution. According to the Hume-Rothery rules, the necessary conditions for a replacement alloy have to be as follows: the same crystalline structure of the elements that are mixed, atomic radius that is not different in more than 15%, similar electronegativity, and same valence or oxidation state. When we substitute solid solutions, both metals occupy equivalent positions on the network at random, and the change of network parameter, but packaging remains. What kinds or types of substitute alloys do we have? We can either have unlimited solubility, for example, AJ and AU, and limited solubility, for example, zinc and copper. Lastly, we have the hydrogen bonds. The hydrogen bond is a strong intermolecular force. It can only be formed by atoms of nitrogen, oxygen, and fluoride linked to hydrogen. Occasionally, it can also be of atoms of chloride and sulfur linked to hydrogen. Hydrogen bonds are very usually formed in water molecules. As we can see in the picture on the right, there are usually more hydrogen bonds in the liquid state than in the solid one, and lastly in steam. Let's start with the Lewis theory. All molecules that are formed by covalent bonds can be represented through the Lewis structures. We have two types of pairs. It can either be a linking pair, and that means those electrons are used to connect two atoms, whereas a non-binding pair means that pair of electrons is not used to unify that atom with another one. This theory helps us understand the octet rule. This octet rule means that all atoms would rather have 8 electrons in their outer shell. What are some characteristics? Now, when we represent the Lewis structure, all valence electrons must be represented. Generally, all electrons are matched, and the atoms of the second period cannot exceed the byte. Also, it is important to note that some molecules or some atoms can have or can form multiple covalent bonds, such as carbon, nitrogen, oxygen, etc. Now, what are the steps to draw a Lewis diagram? Number 1 would be to count all the valence electrons. Number 2 is to determine the central atom. Number 3 is to draw a single bond to the central atom. 4 is to put all the remaining valence electrons on atoms as lone pairs. And number 5 is to turn lone pairs into double or triple bonds to give every atom an octet or duet. As we can see in this kind of representation of a periodic table, we can see how many valence electrons each atom would have depending on where they're found. Let's do an example. Let's start with sulfuric acid. The first thing we have to do, as we've mentioned before, is count all the valence electrons. Now, we have two hydrogens, but hydrogen has a number 1 valence. Therefore, we multiply 1 multiplied by 2, and that gives us 2. Sulfur has 6 valence electrons, and there's only 1 atom. That means 6 electrons, or 6 valence electrons. And then the oxygen has a valence number of 6, and we have 4 atoms. Therefore, we multiply 6 multiplied by 4, that gives us 24. If we add 24 plus 6 plus 2, we get 32 valence electrons. The next step is to determine the central atom. In this case, it will be the sulfur. And then we have to draw the single bonds to the central atom, which would be the oxygens and then the hydrogens linked to the oxygens. The next step, number 4, is to put all the remaining valence electrons on the atoms as lone pairs. For example, we've mentioned before that oxygen has 6 valence electrons. Now, in this case, oxygen, for example, is linked to the sulfur, and the one that is lone and it doesn't have a hydrogen has 6 pairs, right? But the one that is linked to the hydrogen and the sulfur has only 4 electrons. That means 2 pairs of electrons. Let's calculate the formal charges. The formula is as follows. The formal charge equals the valence electrons minus the solitary electrons minus half of the bonded electrons. What are the formal charges rules? Number 1, the total formal charges must be 0 in neutral molecules or the same as its charge in ionic. The formal charge must be as small as possible, and it must be positive in electropositive atoms and negative in electronegative atoms. And formal charges with the same sign must be separated. So in this case, if we want to calculate it for the oxygen in blue, that would be the one that is not bonded to a hydrogen, just to the sulfur. It would be 6 minus half of 2, and that would be minus 1. And then the green oxygen would be 6 minus 4 minus half of 4, which is 0. And then the sulfur one, which is found in red, would be 6 minus 0 minus half of 8. That would be plus 2. Following the rule B that says that formal charge must be as small as possible, that gives us that the solution is to form a double bond between those oxygens that are single that are not bonded to the hydrogen, and the sulfur. If we make this double bond, we can calculate the formal charges again, and we can see that all of them will be 0. As a result, we can see how the sulfuric acid molecule looks like in a Lewis diagram. Let's have a look at the next example. In this case, it's sulfur trioxide. The sulfur has 6 valence electrons. There's only 1 atom, so 6 multiplied by 1 equals 6. The oxygen, as we mentioned before, has 6 valence electrons. In this case, it has 3 atoms, therefore it's 6 multiplied by 3, which gives us 18. That gives us a total of 24 valence electrons. But we have 6 electrons that are used in bonds. That gives us a remaining value of 18 valence electrons. If you do it by yourselves and calculate the formal charge, you will see that it does not equal 0. But for it to equal 0, we need to create double bonds between the oxygen and sulfur. In this slide, you can see a lot of different examples. Just have a look at them and try to understand them. Like everything, the octet rule has its exceptions. We can have either molecules with odd numbers of electrons or incomplete octets. For the first case, we have an example, which is nitrogen monoxide. And the number of electrons is 5 plus 6, which equals 11. For incomplete octets, in this case, we have a number of electrons of 3 plus 3 multiplied by 7, which equals 24. Now, we can see that there's like an equilibrium between the two molecules or the two representations. The first one is boron with 6 valence electrons, which is found in equilibria with boron with 8 valence electrons, and fluoride is electropositive. This basically happens in some compounds that include boron, aluminium, or beryllium. Another example would be expated valence layers, which happens usually when we have a non-metallic atom of the 3rd period or higher. And here are some examples as well.
Now we are going to talk about resonance. There is resonance in a molecule if there is more than one correct Lewis structure of it. At the end, the actual structure is a combination of all the possible ones. In equilibrium, a hybrid of resonance. In the example, you can see the 2 possible Lewis structures for the ozone molecule, which at the end combine in a single one. Take into consideration that the hybrid of resonance may have formal charges even though the molecule is neutral. A resonance shape is more stable when first, the octets are complete, second, the maximum number of electrons is paired, and third, there is a minimum number of formal charges, which must be negative on electronegative atoms and positive on electropositive ones. Here we have another example, now with the ion NO2+. We have to take in consideration that, as the total charge of the molecule is positive 1, the sum of its formal charges must be this value. In this example, we have 2 possible resonance structures, but the most stable one is the first, as the formal charges are lower in absolute value than in the second one, and also because it is unlikely to have 2 charges of the same sign in adjacent atoms. Let's explain Lewis acids and bases. In a simple way, a Lewis acid is an atom, molecule or ion that has empty valence orbitals and therefore can accept an electron pair. A Lewis base, on the contrary, can give an electron pair.